network covalent atomic solids. The most common one of these, well, I guess not the most common, but a common one is carbon in various different forms. So you can have elemental carbon in several different forms. Those are called allotropes. So graphite is carbon. In graphite, the carbon atoms are arranged in layers. And so each of these has these hexagonal circles of carbon atoms covalently bonded to each other. But then one layer to the next layer is just held together by intermolecular forces. And so that allows the layers to slide past each other, which is what makes it a useful thing for writing with a pencil. You know, the pencil lead, there's actually no lead in pencils. It's graphite, it's carbon. But as you pull it across the paper, you leave some of the graphite behind, and then you're writing. Graphite can also be used as a lubricant for this reason. Graphite is a good electrical conductor because we have an extended pi bonding network happening above and below the plane of this, and that's going back to that molecular orbital theory. And you probably just want to say, yeah, I agree. Enough said. So graphite has a density of 2.2 grams per cubic centimeter. If you put a great deal of pressure on graphite, the carbon atoms will rearrange to form diamond. Diamond has a density of 3.5 grams per cubic centimeter. So a diamond looks very different than graphite, right? Graphite was soft and black and smudgy, and diamonds, when they're cut, are clear and shiny and really, really hard. Here we have, again, this is an atomic solid. We've got atoms here, but they're covalently bonded, this time in 3 dimensions. So diamonds form naturally underground where there's a lot of pressure. You can also synthesize them. It takes something like 50,000 atmospheres of pressure and 1,600 degrees Celsius. So, it's not a simple matter, but it can be done. The structure of the diamond unit cell is similar to that zinc blende cell that we saw, that was a face-centered cubic, and then it had 4 atoms in those tetrahedral holes. So that's what's going on here with the carbon. May or may not be able to see that. It just kind of looks like a mess. But what's happening here is that each of these carbons is bonded to 4 other carbons. And remember, we learned that carbon likes to form 4 covalent bonds, right? So here all the carbons are really happy, just by themselves, no hydrogen needed. They're just making this. So really hard and has a really high melting point and conducts heat very well. So this is diamond, they don't use the really nice diamonds. They use the little scritchy, scratchy pieces. But diamond is a good abrasive. You put it on drill bits and saw blades and stuff. It conducts the heat away, which is good because then you don't start your wood on fire. But it's also very hard, so it cuts well. High pressure favors the formation of diamond from graphite. What can you conclude about the relative densities of the 2 substances? The diamond is more dense, the graphite is more dense, or you can't tell because you need more information. So we're taking graphite and we're putting immense pressure on it to make the diamond. Would that make it more dense or less dense? If you're squishing it together, it would make it more dense, right? So diamonds are denser than graphite. Carbon can also do some other cool things. Back in the 1980s, they discovered fullerenes. also known as buckyballs. Buckminster fullerene is kind of like a soccer ball cluster is 60 carbon atoms, and they have these hexagonal rings here, and they're all covalently bonded to each other, and they make a ball. So that's a buckyball. And you can get these as small as 36 carbons, as much as 100 carbons or more. So this looks a lot like a sheet of graphite, right? But the graphite was just very loosely held to the other sheets of graphite. You can also, this is the graphene that they discovered. And so graphene can be made into a ribbon or a tube, nanotube. You can make multiple nanotubes and nest them inside of each other. So what's really awesome about this stuff is those nanotubes are 100 times stronger than steel and 1/16 as dense. So they're a lot lighter and they're much stronger. So this is where, if you go buy a high-end bicycle and the frame is graphite, you want a bike frame made out of pencil lead? That doesn't seem like a good idea. Well, it's not really graphite, it's graphene, but regular people don't understand what that is. But that's what you're going to see in your expensive bicycle frames, because really strong and a lot lighter. Golf clubs also. You can take these nanotubes and make tiny, tiny wires, because these things conduct electricity.
Would it be some of the diamond or no?
Well, see, the thing about a diamond is it's brittle. And so that's why you can get it to, you can cut it with those faces.
Yeah.
Whereas this isn't going to be brittle like that. Another type of network covalent atomic solids are silicates. And so these are atomic solids, even though we have two different kinds of atoms in here. We've got oxygen and silicon. And so the formula unit here is SiO2. That just means that for every silicon there's 2 oxygens. But this is not an ionic compound. Silicon is not a metal. And essentially it forms one giant molecule. And this is, silicates make up about 90% of Earth's crust. So sand, mostly silicates. And so you can have different kinds of silicates. Quartz is one form. These things are also used to make ceramics and cement and glass and all kinds of other useful things.